We just described the conditional factor demands. The conditional factor demands are how much capital and labor do I, as a firm, employ or hire when I'm trying to minimize the cost to meet a production threshold, some production target Q. Right, so contractually obligated to meet production at a level Q or higher to produce Q iPhones or Q whatever standardized tests or Q hours of content for Netflix, and I have to decide what's the best way to do that. And best to me is the way that costs the least, and so I choose my inputs to be minimum cost minimizing. And of course, this is exactly the same as Hicksian demand, compensated demand, right? It is minimizing some linear function, price times a vector of inputs or demands, subject to some function being above a target, some function being positive. And that is exactly expenditure minimization. It's exactly this thing of cost minimization. So those are the same thing. Because it's the same thing, we can define a cost function, which takes a price vector and a target, and that's going to be the same thing as our expenditure function, right? So our expenditure function E took a cost or a price vector and a utility target. The cost function takes a cost vector and a production target, but otherwise it's exactly the same. And the cost function is defined as the vector of costs times the input, the conditional factor demand. So the vector of cost is the cost of capital times the price of capital. The cost of labor is the cost of labor per unit times the amount of labor hired. And the total cost, or the cost function, is the optimized quantity when I'm choosing capital and labor optimally in order to meet the level Q when prices are given by the vector C. How much does this cost? What is the minimum cost I can produce this at? Now, I had this old theorem floating around from weeks ago. Remember something about the expenditure function, and it was non-decreasing in P, it was homogeneous of degree 1, it was concave, continuous, blah, 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 blah. Hicksian demand is the derivative of the expenditure function with respect to prices. And this is a very nice theorem. It had a lot of informational content in it. We went over a lot of things here. We talked about the comparative statics in detail. Why would we have non-decreasingness? Why would we have homogeneity? Why would we have concavity? And then we showed that, from these things we can derive, from points 3 and point 5, we can derive the law of compensated demand. This was a brilliant theorem, sort of at the core of our expenditure minimization lectures. And I just said that what we're doing now is exactly expenditure minimization, so I have exactly the same theorem. The exact same theorem, just replacing E's with C's and P's with C's and U's with Q's, and otherwise keeping everything around the same. The expenditure function is non-decreasing in C. If costs go up, the cost of the inputs go up, the total cost, the optimal total cost I expend making Q units or more of output cannot increase, right? It has to, it cannot decrease. It must weekly increase. It can stay the same, but it can't go down. If all the costs double, the cost of labor and the cost of capital doubles, well, the trade-off between these two costs is the same, right? The ratio at which I can trade one for the other is the same, in which case I'm going to choose exactly the same vectors of inputs, but my cost will now be twice as much because the costs doubled. So that means that it's homogeneous of degree 1 in costs, right? So when I double the costs, my minimized expenditure, my minimized cost function doubles as well. It's concave in C. Remember, we looked at those pseudo expenditure functions. We said that you could keep doing what you're doing. When prices change, you could just employ the same amount of capital and labor as you were before. And the change in total cost would be a linear change according to the change in prices, right? Because it just scales up and down. When the prices go up, the total cost goes up exactly by a linear component depending on how much you're employing of that particular good. But of course, you don't have to stay at the same level. You could substitute one input for the other if the relative ratios become advantageous to do so, in which case it could be that you have a lower than linear increase in costs. And if something is always less than linear in its increase, then it's concave. That's the definition of concave. That's why the second derivative is negative. It's less than linear increase. It's continuous in C. That should be no surprise. Everything's sort of continuous. That's just Burgess' theory of the maximum. And then finally, the conditional factor demands are the derivatives of the total cost function with respect to the relative inputs, right? The derivative with respect to CK gives you K star, and the derivative with respect to CL gives you L star. So this is exactly the same theorem. I encourage you, if there's any confusion about why these things are true, to go back and look at the lecture on expenditure minimization, look at the explanation of this theorem in those lectures, and notice that up to a relabeling of the parameters, calling things C's instead of P's, we're dealing with exactly the same mathematical objects, and so the interpretation and the intuitions, while we're talking about different things, really remain the same, right? The mathematical intuitions are invariant. So let's do one example. By now, you should be able to pump these out in your sleep. A firm has a production function, which is just the minimum of K and L. Needs one labor and one computer to write some code. An extra coder without a computer is useless. A computer without a coder is useless. You need the minimum 1 and 1. The firm wants to solve the problem of spending the least amount of money to produce Q units of output, Q lines of code, and that just means that the minimum of K and L has to be greater than Q, and we're going to assume that we have strictly positive costs, right? Neither capital nor labor is going to be free. So at the optimum, of course, if K was larger than L, the firm could clearly lower costs by reducing K, right? These are going to be nice L-shaped isoquants, and we know that we're going to be at the kink. If you were employing more capital than labor, you could just move down the isoquant, and you'd be lowering your costs, right? But you wouldn't be doing anything to the production output. So obviously, you could lower costs unless you're at the kink. By an analysis argument, L can't be greater than K, which means we're left with K is equal to L is equal to Q. And so the cost is then obvious. It's Q times CK times plus CL, right? For each unit Q that you're producing, you're hiring 1 unit of labor and 1 unit of capital, which means the cost of that unit Q is going to be CK plus CL for 1 unit of each thing, which means that to produce Q units, you're spending Q times CK plus CL. Now, we could look at the optimal choice as we move to different levels of production, and this is called the firm's expansion path. So imagine that for now, the firm needed to be on the isoquant Q1. So Q1 is a level of production. Maybe that's producing 10 units of output, 10 iPhones. And the cheapest way to do that is by hiring K1 units of capital and L1 units of labor, and ending up at that point K1, L1, which is the furthest point closest to the origin. Now, we want to know, how does the hiring of K and L change as we increase this quota, as we increase production, right? As we expand the firm. That's why it's called the expansion path. So what does it mean to expand the firm? It says, well, we're not going to produce 10 units of output. We're going to produce 20 units of output. So instead of being on the isoquant Q1, we want to look at the isoquant Q2. Well, at Q2, we're going to have to hire different amounts of capital and labor than before. And usually, we're going to have to hire more of both of them because we're producing more units. And so we end up at this point in the middle, which would be, if it was labeled, L1, L2, K2, right in the middle. And we can do this again, and we can move to the next one. We see that at Q3, at 30 units of output, there's yet another point. And we don't have to do this for a discrete number of things. We could do this for every possible output, right? So for every Q, we could look at what is the conditional factor demands of that corresponding to that Q. What is the cheapest way to produce that particular cost, that particular output? And we could just draw these on a graph, right? So for every amount Q, for every isoquant, there's some point which is the cost minimizing point, and we could just connect these with this line E. E traces out the expansion path. That's how much capital and labor you're employing as you grow, as the firm produces more output. Or I guess less output if you're looking at E going the other way, right? It shows the relationship between capital and labor and the quantity produced. Now, it might be tempting to assume that as the firm expands, it increases its production, its demand, for both inputs, its factor demand, right? So if you tell the firm you have to produce twice as much, you're going to at least want weekly more capital and weekly more labor. You're never going to want less capital or less labor. Just like how we had inferior goods, nothing in this particular model rules out the possibility of demanding less of a particular good when you expand production. So a good, an input, is called input inferior, if when you increase the production target, it actually decreases, right? So in other words, the derivative of the conditional factor demand with respect to Q. As Q increases, the conditional factor demand decreases. That's called an input inferior good. And it is possible in this model, and you can see you can draw some nice convex, everything here is nicely behaved, right? These are convex isoquants, so it would be a quasi-concave production function. So this isn't like we have diminishing technical marginal rates of substitution, or whatever it is, MRTS. So this is a nicely well-behaved utility function, and yet you can see that as you're increasing the amount produced from Q1 up to Q2, up to Q3, up to Q4, at first you're increasing the quantity of L demanded, and then eventually decreasing the quantity of L demanded. It doesn't really make so much sense with capital and labor, but a good example of an input inferior good would be things where there's high substitutability, but relatively large sort of fixed costs. I mean, not in a serious sense fixed costs, but like the actual per unit is much larger, but the return is larger. So, if I'm hired to do a very small construction job, I might hire a lot of labor and a couple of people with shovels, right? And so my demand for shovels is relatively high. But if I'm suddenly going to be digging out an arena, I'm not going to be doing it by hand. And so instead of using any shovels, I'm going to substitute away from shovels and use, large-scale construction equipment, backhoes or something like that. So I move away from shovels and towards backhoes because there's this substitutability. But for small-scale jobs, a backhoe is really way too expensive to employ, and so I'm not going to do it. So this kind of thing might have a that's sort of the kind of arena in which we might see this backwards bending type expansion path. So a last point in the lecture on cost functions is that it's often useful, instead of looking at the total cost function C, capital C, to look at per unit of output measures, right? So not the cost in total, but the cost per unit of output, which would be something like an average cost or a marginal cost. So the average cost function is just the total cost of producing Q units optimally divided by Q, right? So that's the cost per unit of output when you're optimizing by minimizing costs. The marginal cost function is the same thing, not the same thing, it's the derivative of the cost function with respect to Q. And so, in other words, it's if I increase my production just a little bit, how much do I increase my costs by, right? So if I want to produce a small amount more of output, how much is that going to raise my total cost? So we could take a look just at some maybe how these things relate to each other. So if we start out with a total cost function. So if we have Q and we look at the total cost function and it's just linear, that's supposed to be linear. Maybe I'll try to make it a little bit more linear. So that means that for every unit of output, there's a constant increase in the amount of cost, right? So this is the cost function is a linear relationship, has a proportional increase to the amount produced. In this case, we have something like this is a constant returns to scale type production, right? As I hire more stuff, I get exactly the same output each time I hire it, and so of course it's going to be that the cost is going to be increasing sort of in a linear fashion. So if I have this constant returns to if I have this constant returns to scale output, I'm going to have something that looks like this with a linear cost curve, total cost curve. So this is my C star. This is my total cost. Then we have a constant marginal cost, and this is actually equal to the average cost, right? The average cost is the same. The marginal cost is the same. At every point, the marginal cost is just the slope of this line, right? If I increase production by a little bit, the cost increases according to the slope. The proportion of the amount more in cost I pay is the slope of that total cost line, which by nature of being a linear function is constant. The slope is constant. And if you think about it, if you're constantly paying the same amount, so every little bit costs the same amount, then the average, of course, is equal to each little bit, right? I mean, it's that's just a mathematical identity. if the marginal cost is constant, the average cost has to equal the marginal cost, and so the average cost and marginal cost functions are actually the same. Often we think of the total cost function as sort of having a cubic type look. So something that's like a little bit like this. So it's sort of concave in the beginning and then convex in the end. So this, remember that we said that the cost function is concave. We said it was concave in C. This is concave or convex in Q. Okay, so we're talking about concavity relative to particular inputs of this function. So in this graph, we're talking about Q being on the x-axis. We're saying as you produce more, there's a point at which you're producing more efficiently, right? Producing one baseball bat is very costly. You got to open up a factory, find whatever, there's a bunch of stuff you need to get done. Hire a laborer, pay him for the whole time, train him how to do it, and you produce one baseball bat. To produce the second baseball bat, there's not so much extra, right? The marginal cost then becomes much smaller because you already have the labor, you already have the factory, whatever. They can just work for a little bit longer. So there's this period where the marginal cost is falling, right? The marginal cost is falling, and that means the total cost is getting shallower, right? The slope of the total cost is falling, right? So there's a period where the marginal cost is falling, and it's followed by a period where the marginal cost is increasing, right? The marginal cost is increasing because eventually it becomes harder and harder. Like you're using all the easy to access wood, or you've used all the laborers. You have to start paying people more because you can't find. Well, that's more of a the cost of the inputs is supposed to be the same. It just gets crowded in your factory, right? And so you have to employ more and more stuff to get the same technological benefit from it. So there comes a point where the cost starts to increase faster as you increase the production quota, as you require this company to produce more baseball bats. It becomes more expensive to produce each one, right? So there's this initial period of increased technological trade-off or productivity, followed by a decrease in productivity, which is this decreasing marginal product productivity. We discussed in the first lecture sort of why we might think that there's decreasing marginal productivity eventually, right? Maybe not always, but eventually. In fact, we had that cubic function which produced exactly this kind of graph. That means that there's a period where the marginal cost function is falling and then it's increasing, right? So this is marginal cost. So the marginal cost is then a quadratic, right? And we can see that, it's because it's a derivative of a cubic. And the average cost function, is also sort of quadratic, or it doesn't need to start at the same place. Maybe it looks like, well, maybe it does. And this point where they cross is the minimum of the average cost line. Right? Remember, we said the same thing about marginal production and average productivity. That as long as the marginal cost is below, so for this whole period, right? Maybe I'll do it in a different color. So for this whole orange part, so in the orange part, the marginal cost is less than the average cost, right? When marginal cost is less than average cost, each additional unit costs less than the average that it costs to produce. So to produce the next baseball bat costs less than the average so far it's costed to produce baseball bats, right? So if I add something new to an average that's smaller than the average, then that brings down the average, right? So if I have a bunch of grades in a classroom and I add one more student, if he's below average, then the average in the class goes down. If I have a bunch of costs of baseball bats and I add a new one and the marginal cost, this new baseball bat, is less than the average, then it brings down the average cost. So that means that in the orange region, average cost is going down. Then we have the purple region. The marginal cost is above the average cost, right? And for exactly the inverse logic, if we add a new cost of a baseball bat and it's higher than the average cost of baseball bats, now we're increasing the average cost. So that means the average cost is increasing, which means at this point where the marginal cost and average cost intersect, So when marginal cost equals average cost, this is the minimum of the average cost. And that's actually true up here also. It's just that the minimum is everything, right? Every point is a minimum. So that there's nothing incongruent between these two examples. So that's all I have to say about that. Go back and check the news again.